Today I'll be doing 7-1, part 1, talking about exponential growth and decay. Our learning targets for today are I can determine the multiplier for exponential growth and decay, and I can write and evaluate exponential expressions to model growth and decay situations. An example of an exponential equation is bacteria grow by splitting into 2. If 25 bacteria are currently on your cell phone and the entire population doubles every hour, how many bacteria would there be in T time? So this equation is considered exponential because the variable is an exponent. So that is what is going to determine if something is exponential versus something is quadratic or linear and so forth. So we can see that we have a t as our exponent because we don't know what the time is, so that can constantly be changing. 25, if we can see, is our initial amount of bacteria, and then 2 is our multiplier. It's how often it's going to increase. So in this case, it's doubling every hour. So every hour it's getting 2 times bigger. So our base here is a 2, and this 2 here is called our multiplier. So the base of the exponent is called the multiplier. Here, the multiplier is 2 because it is doubling. If it was tripling, it would be 3. 4 times as large, 4, and we're going to look at some other types of multipliers that we're going to see often in the types of problems we're going to be looking at. So there are 2 types of multipliers. We can be looking at exponential growth or exponential decay. So exponential growth is what we are used to seeing. We, in the last unit, looked at graphing exponentials, and a graph of an exponential starts off low and then gets increasingly faster going up. Where exponential decay is going to start up high and get smaller as we approach 0. So exponential decay is going up and exponential decay is coming down. Remember, we always have asymptotes when we're talking about exponential growth and decay as well. So for exponential growth, we're going to add the rate of growth to 100% because 100% is what we start with, and then we're going to be increasing, in this case, by 20%. So we would have 112%. When we talk about a multiplier, we always are going to write it as a decimal. So 100% would be 1. So if we had 112%, our multiplier, we're going to move our decimal twice. So our multiplier would be 1.12. For exponential decay, we're going to subtract the rate of decay from 100. So here we had 100 plus 12. Here we have 100 minus 7. So if we take 100 minus 7, we have 93. And if we change that to a decimal, our multiplier is going to be 93 because we want to take away 7% each time we're multiplying. So for exponential growth, you add to 100, exponential decay, we're going to subtract from 100 in order to get our multiplier. So some practice. It says determine if the following equations represent exponential growth or exponential decay. So we have 6 equations here. So what I'd like you to do is take a second, pause the video, write these all down, and determine exponential growth or decay based on the equation. Okay, so for each of these, to determine if it's growth or decay, you always look at the multiplier. And the multiplier is the base of the exponential. So it is what is the base of our exponent. So if I were to go through and look at all of these, 0.5 is my base of my multiplier. 5 is my multiplier. 4, 2, 0.9, and 0.3. The numbers that we have out in front here, those are, remember, our initial value. So that has nothing to do with growth or decay. That's just how much are we starting with. So if I were to look at number 1, if it is greater than 1, it's going to be growth. If it's less than 1, it's going to be decay. Because remember, I'm adding or subtracting to 100. So number 1 would be growth. That is not true. Number 1 is less than 1, so this would be decay. Number 2 is greater than 1. It's doubling, so that would be growth. 3 is greater than 1, so that would be growth. 4 is less than 1, so it's going to be decay. 5 is getting 4 times larger, so that would be growth. And 0.3 is less than 1, so that's going to be decay. So we're always looking at the base of the exponential to determine growth or decay because that is our multiplier. Now we want to determine the correct multiplier for each rate of growth or decay. So if we're given decay, we're subtracting from 100, growth we're adding. So for number 1, I have 9% decay. So I'm going to take 100, subtract 9, and I would get 91. And if I turn that into a decimal, my multiplier would be 0.91. 2, I have 3% growth, so I'm adding. So I have 103, and if I change that to a decimal, I have 1.03. So go ahead and pause the video and try number 3 and 4. All right, so number 3, 11% growth, we're going to add 11 to 100, and we're going to get 111. If I change that to a decimal, my 1.11 is my multiplier. And for number 4, I'm subtracting from 100. So if I'm subtracting from 100, 5.9, I get 94.1. And changing that, I get 0.941 as my multiplier. So these are going to become important when I write my equation. So now we're going to get into actually writing exponential functions. And our general exponential function is y equals a times b to the t. So y is our end amount, our end population, our end dollar amount, our end bacteria amount, whatever our end goal is. A is going to be your initial amount, what you start with, and B is your growth or decay factor, that multiplier that we just worked on finding. We're going to have to find that within the context of the problem to be able to write that as the base of our exponential. And then T is going to be the amount of time. So after we're able to determine if an equation is growth or decay and find that multiplier, we want to actually be able to solve exponential equations. So an example here would be the population of a city was approximately 520,000 in the year 1990 and was projected to grow at an annual rate of 2.6% per year. Predict the population to the nearest 10,000 for the year 2006. So per our equation, we have y equals our initial value times our multiplier raised to the amount of time. So finding all these pieces of information within the context, our final value is what we don't know. That's what we're solving for. Our initial value is we started with 520,000 people. Our multiplier is 2.6%, and it is growing at 2.6%. So our multiplier is growth, so we're going to add 2.6 to get 102.6. So if I change that to a decimal to be my multiplier is going to be 1.026. And now the amount of time, it says we started in 1990 and we want to predict what it was going to be in 2006. So we want to know how far apart, how many years have elapsed from 1990 to 2006. So if we take those and subtract them, we have 2006 minus 1990. That's going to be 16 years. So now to write our equation. Well, we don't know our final value, so we're trying to figure out what our exponential is equal to. Our initial value is 520,000. Our multiplier is 1.026. And we want to predict what it's going to be after 16 years from when it was 520,000. So now to figure out what our final value is, what the population is in 2006, we just have to plug this into our calculator. So if I plug this into my calculator, I have 520,000 times 1.026 raised to the 16th power. Remember, I use that caret button under clear in order to raise something to the power. So when I plug this in, I get 784,081. Now, if I follow directions, it says to the nearest 10,000. So I would cut it off at 784,000 as my final answer. So it grows from 520,000 to 784,000 people over the period of 16 years. And our final example here has two parts to it. A says what value should the analyst use for R, and B, what does the analyst believe the value of the stock will be at the end of 3 weeks. So A is going to have to deal with our first part of the lesson, and B, that second part, writing an equation. So I'd like you to read through this and try A and B while the video is paused, and then play the video for the answer. All right, so we have this problem that says the stock price of one share in a certain company is worth $360 today. A stock analyst believes that the stock will lose 28% of its value each week for the next 3 weeks. The analyst used the equation V equals 360 R to the T power model to model the value V after T weeks. So A says, what value should the analyst use for R? So R here, since that is the base of our exponential, that's going to be our multiplier. And our multiplier has to do with our percent increase or decrease. So here it says a stock analyst believes that the stock will lose 28%. So this would be decay. So our multiplier, we're going to take 100 and we're going to subtract 28. So if I take 100 and I subtract 28, I get 72. And if I change that to my decimal, the value for R should be 0.72. So that means my equation is going to be V, the value, equals 360, my initial, times 0.72, my multiplier, raised to the T power, depending on the number of weeks we have. So for B, what does the analyst believe the value of the stock will be at the end of 3 weeks? Well, since T in this is weeks, we're just going to take 3 and plug it in for T. So we have 360 times 0.72 raised to the 3 power is what the value of the stock is going to be after 3 weeks. So if I take this and I plug it into my calculator, Remember to raise it to the third power. Use that caret button right underneath clear. Raise it to the third power. And I should have 134.37 because I have 369, round that up to 37. 2 decimal places because I'm talking about money. So $134.37 would be the price of the stock after 3 weeks. Because it is decay, it's going down. That does make sense. So if I were to think about what this would look like on a graph, it's going to be decay. It starts up higher and it gets lower. And if I'm thinking about this as a real life context, it makes sense that my asymptote is here at 0 and that this graph is never going to go below, because I always have to be above 0 for a stock price. And 360 is going to be my y-intercept. My initial value is always going to be my y-intercept because that's my starting value. So that's where it's at, and it decreases from there. We don't care what's over here because we're just looking at where we start and what the trend is going to be afterwards. So your initial value is always going to be your y-intercept, that starting value.